We're ready for problem 3. All right, problem 1 took a long time, right? We had to figure out what the rate law actually was from the experimental data. You'll have one like that, lots of points. Okay, go over that one. Problem 2, a little quicker, not so bad. We didn't have to worry about having the rate law because we were told what the rate order was, so we didn't have to figure out the rate law to get the rate order. Nice. This problem here, I'm using rate order, number 3. I'm looking at number 3, in a little different way. Okay, so what are you talking about? Well, remember what rate order means. Rate order is the add up all the exponents and you get the complexity of the reaction. And it has something to do with, the effect, not something to do with, it does have to do with the effect of concentration on rate. So if you had a 0 order rate, which you can, the concentrations, you can have the exponents on top being nothing. What does that mean? That means the concentration is irrelevant to the rate. So if you have a 0 order rate, then that has no effect on the concentration. You could double, triple, whatever the concentration, and the rate won't change. That's a 0 order. A first order, the first order, Star Wars, that one is a direct relationship. If it's a 1 for an exponent, then that means if you double the concentration, you double the reaction rate. If you triple the concentration, you triple the reaction rate. Okay. Second order would mean that either you have 2 1 exponents or 1 2 for an exponent. And that effect would be identical, meaning that if you have a second order rate, it's a squared relationship. So if you double the concentration, square it, double 2, square 2, 4. It would be 4 times the reaction rate. If you tripled the concentration, square that, square 3. 9 times the reaction rate, and so on. You could actually have a cubed reaction rate. Yes, you can. So if you doubled the concentration with a cubed rate, it would be 2 times 2 times 2, which is 8 times the reaction rate. So that's what the order means. It has to do with, how the concentration is going to affect the reaction rate mathematically. All right, let's dive into this problem. This problem here says you've got this reaction. Phosphine is going to decompose. There's just one reactant, that's the phosphine. It decomposes, and it tells me that it's a first order reaction. It does? I'm pretty sure I saw it on there. Yeah. Okay, the first order rate constant. So this is telling me it's a first order reaction. So what does that mean? That means that the phosphine, being the only reactant, if you double the concentration, you double the reaction rate. Okay, it's a direct relationship. Now, check this out though. This is a different problem. Of course it's a different problem. It's number 3. No, I mean it's different. Okay. This problem says, okay, the half-life of the reaction is 35 seconds. Half-life? What is that? I've heard that before. Oh, that's a video game it came out 15 years ago, and it was awesome. And I love video games. And they would, so we're going to do a video game. No, we're not. I wish we were, but those are fun. But yeah. Oh, chemistry is fun too, but I mean, not a video game. Oh, radiation. I've heard of half-life that has to do with radiation, right? Correct. Radioactive materials have a half-life. It tells you how quickly they break down. Something like uranium, you find in power plants, has a half-life. Well, one isotope has a half-life of 5 million years. That means it's going to be around for a long time. Some half-lives are really fast for radioactive materials. If you get injected with a radioactive or radiometric dye, usually to track something in your body, they look at it and see how things are moving. That has a very short half-life, which is good because you don't want radiation in your body for a long period of time. That could cause some problems. So half-lives can vary from milliseconds to millions of years. All right, so half-lives have something to do with how fast something breaks down. That's exactly how we're going to be using half-life in chemistry. What? We're dealing with radiation in chemistry? No, that's actually a unit called nuclear chemistry. We're doing chemical reaction rates and how fast they happen and how fast the reactants break down. See, reactants have got to do their thing, right? Spit out some product. And the half-life is how long it takes half of that to go away. So radioactive half-life and chemical reaction rate half-life are the same thing, so to speak. In other words, how long it takes for half of the reactants to be gone bye-bye, okay, formed and make product, or broke down and made product. Okay, so the half-life. So this reaction tells me that it's 35 seconds for the half-life of the phosphine. What does that mean? That means after 35 seconds, half the phosphine is gone. Yes, Billy? Oh, so that means, let's see, 35 times 2 is 70. So after 70 seconds, all of it's gone, right? Because 1/2 goes away in the first 35 seconds, and then the next 35 seconds, it's all gone. So the whole reaction takes 70 seconds. No, Billy. Hate this class. Sorry, Billy. I mean, you're okay. At least you're thinking, Billy. I appreciate that. I do. But it doesn't work that way. Okay. For every half-life, you lose half of the remaining reactants. So in this case, with the phosphine, after 35 seconds, half of the phosphine is gone. After the next 35 seconds, another half of the remaining is gone. So if you had 100 grams to start, after 35 seconds, you got 50 grams. Then after another 35 seconds, you have 25 grams. After another 35 seconds, you have 12.5 grams. After another 35 seconds, you have 6.25 grams, and so on. That's how it works. Okay, so that's the concept of half-life. It's not too bad of a concept, really. But, so why are they telling us half-life in this? What's the point of that? What's this half-life thing? What do we have to do half-life for? Well, sometimes you need to know how long your reaction is going to take place. What can you expect? How long before the reaction runs out of steam and is done? Or how long does that take place? So if I know the half-life, I can figure stuff like that out. And that's what this problem's about. Yeah. Okay, let's do A. Okay, what is the first order rate constant for this reaction? So A wants to know the rate constant. Rate constant? We had to go through rate laws and experimental data to figure that out in the first problem. Oh no. No, don't worry. Take a look at your equation sheet. Okay, you should go to Essential Documents and get this. Here's all the equations we need for the first part of the course. The thermodynamic equations that we're going to use so far. We got a lot more of those to go. Then here's the colligative property, and here are the reaction rate law equations. Yes, that has an equation on it. If you look down here, actually I put it out of order. I didn't put it in order. I like to put them in the order that I'll do my videos. But I was just writing them down, and they were coming to me randomly. So let's see. Okay, that one's the rate constant. Did that. This one we haven't done yet, but we're going to, and this one we're going to use right now. So we're using this one before this one, even though this one is below that one, and this one is A, and this one's B. Okay. There's the half-life equation right there. Look at that. What is it? Half-life, and that means half-life. Okay, T is for time. Half is the time it takes for half the substance to go away. Is equal to 0.693. Sometimes I just round that to 0.7. Close enough for government work. And here, K. Close enough for this class. If you're in analytical chemistry, you would not want to be saying that. You want to be close. Okay, now, look, K, that looks familiar, right? That's the rate constant. And we want to find the rate constant for part A of this problem. All we need is this number, which we have. This is calculus derived. Don't worry where it comes from. Just know how to use it. And that is the half-life. And we were given that. So we can arrange this to solve for K. We don't have to go through all that experimental data like we did in part 1. Well, not all problems are like that. There will be one, though, on the test, so you do need to know how to do it. Okay? So this is 0.693 divided by the half-life time. The half-life time has to be in seconds. If it's not, you have to convert it to seconds. So if you were given a half-life of 2 days, you got to convert it. Okay? But don't you worry. I am here for you. Our problems will be in seconds. No conversions necessary. Thank you. You're welcome, Billy. Okay, so let's go ahead and solve this. This should be pretty quick. 0.693 divided by 35 seconds. I made it 35.0. I'm not too concerned with significant digits. Just give me a nice number that's not the whole calculator number. That annoys me. So let's see. The 0.693 divided by 35, 0.0198. I'm going to round that to 0.02 units. This is a number, so it doesn't have any units. This had the units in seconds. Remember, it was a half-life, it was 35 seconds. So if you were looking at the units for this, it would actually be a weird one. It's 1 over seconds. Remember I was saying earlier, K-value units are kind of weird. They're all different depending on the stuff. So don't worry about the unit. You get the number. We're good. We're good. So 0.02, that's our K-value. A, all solved. Okay, part B. I'm going to erase this, get room for part B. We're going to have to remember that number. Will you remember that with me? Okay, remember that. We're probably going to need it. 0.02 is our K-value, our constant. Okay. Part B. I knew you were going to be a good classmate. Yes, I knew it. Okay, where is the questions? Here. There we go. Okay. Part B. The time required for 95% of that phosphine to break down and decompose. The time required. Time required. Oh man, that's time. We don't have any equations with time. We don't have that. Well, we had the half-life equation up here, right? And the half-life was a time, right? That T1/2, that's a time. Is that the equation we used? No, because that's the half-life value. We need to figure out how long it takes, and it could take, I don't know, a day, a year, some reactions, we don't know how fast that. We need to figure out how long it takes 95% of the reaction to be complete. That's not the half-life. So that equation's not going to work. Now we need another equation. Oh, itchy nose. Ooh. Okay, might be sneezing soon. You just wait. There we go. Equation sheet. Equation sheet right there. That equation right here. This is actually the same equation here and here. It's just rearranged. This is what I call the working equation. Typically, you're not going to have it set up like this. It is calculus derived again, but so this is the one that is usually the version of that you want. So right there, that equation is going to work. That has time in it. It has time in it. In fact, that's called the first order. The first order. I just can't help that. Just do it. Star Wars. First order reaction time equation. So you might want to write that down. Just maybe write first order above it, because we do have an equation down here that's coming up for the next problem. That's the second order equation. That's your first order equation right here. That's your second order. So maybe jot that down. Okay, so that equation, all right, let's take a look at it. All right, okay. Okay, that's time, that's plus, that's ln, that's a, and that is 0. Okay, that equation is an algebraic equation. And it looks all complicated. It's got ln in it and everything. It's not. It's really not. ln means natural log. You might not remember that. Logs. Kids love log. Ren and Snippy's log. You probably don't even know that one either. But you need one of these. You need a scientific calculator. If you don't have one, shame on you. Go get one. You need one because it has natural log and log button on there, and you're going to need those in this class. Big time logs coming up with pH and acids and bases. Get yourself one of these. Actually, the cell phone has this on there. Cell phone will work. Okay, so all you need to do is just know how to hit the ln button. If you can hit the ln button, you're good. You don't need to know that logs are exponents. That's what they are. They're exponents, but just hit the button. Hit the button. Let's put stuff into our equation and solve for time. Now, where is time? There's a t here and a t here. Which one do we use? That one. That is the t. That means the time of the reaction. This is what I am solving for. It wants them to know how long it's going to take, the time for 95% of our one reactant phosphine to break down 95%. Almost all gone. Not all gone, but almost all gone. So I'm solving for this. That means I need that, and I need that to put in my equation as variables. Let's do it and get her done. You remember what square brackets mean? Concentration. We need the concentration of, and remember, these rate laws are all about the reactants. So we're always looking at the reactants. In this case, reactant. Okay, there's one reactant. It's a first order rate law. So, okay, it tells me that. So I use the concentration of phosphine. Let's find the concentration of phosphine on the sheet.
I've been looking since you've been babbling, and there isn't a concentration of phosphine. They don't give it to us.
They do. It's just kind of hidden.
Hidden where?
In the percent. That's going to give me the concentration of phosphine.
I don't get it.
Okay. I always tell my students, if you're ever given percentages and you need to get those into grams, just take out the percent and put grams.
You can do that?
You can do that. If you have to have, you give them a percentage and you need concentrations, take out the percentage and put concentration. Put M meaning molarity, concentration.
You can do that?
Yes, you can. Okay, here's what we know. 95% of this stuff is gone, meaning you have 5% left out of 100. 5% left out of 100. And oh, by the way, that 0 means at the start. 0 means at the start, times 0. At the start, our concentration was 100%. We had it all. So I'm going to assume 100 molar. I'm going to assume 100 molar. I can do that.
You can't do that. What if it was only 2 molar?
Then you'd put 2 molar in here.
Well, that's not 100.
Correct. But over here, this means the concentration of the reactant, in this case, the phosphine, at the point in time that I'm looking for, which means when there's only 5% left. Remember, 95% is gone. So we have 5% concentration left. And 5% out of 100 is 5. So I'm going to use 100 as my starting concentration, meaning 100%. And 5 is my ending concentration, meaning 95% is gone, so I have 5% left.
But what if it were 2 molar to start?
Then you put 2 here, and you take 5% of 2, which is like 0.01, yeah, 0.01, and you put that in here.
You'll get a different answer then.
No, you won't. You won't. Proportionally, it's the same. It'll come out to be the same.
I don't believe you.
All right, well then you go ahead, Billy, and you solve using the 2 and 5% of 2, which is going to be 0.01. You go ahead, you do that, and you see what you get. Make sure you're careful on the algebra, and we'll see what we get, and we'll compare at the end.
Okay.
All right. Let's do this problem. So, I've got this. Oh, okay, we figured it out from part A, remember? 0.02. So I'll go ahead and put that right in here. 0.02. And I'm going to bracket that off. That negative goes with that. We have to remember that. Don't forget that negative. So now it's an algebra problem. It's a relatively simple one. We just have to have the calculator so I can get the natural log of 5. So on my calculator, I'll hit the LN button and go 5, close the bracket, and enter. And I got 1.61, right? 1.61, yeah, 1.61. 1 equals 0.02, negative 0.02. Don't forget that negative. Sometimes students don't like using a variable like t. They'll want to put an x in there because they're used to algebra, the unknown being an x. That's fine. Put an x in there. Well, I'll do that. I'll put an x in there for you. So this is what we're trying to find is x. And then plus the natural log of 100. So I got to get the natural log of 100. Natural log 100, enter 4.61. All right, we'll round that to 4.61. Okay, now it becomes a relatively simple algebra problem. I'll get the x by itself, isolate x, subtract 4.61 from each side. Nice. That is negative 3. Negative 3, don't forget the negative. Negative 3, all right, equals negative 0.02 times x. Okay, all right. Dividing this by that. So we're going to divide, isolate the x, divide by 0.02. Negative divided by a negative. It's positive, so those negatives go away. So that's 3 divided by 0.02 equals x. And that will come out to b, goes in there, 1 and 2. So go to 150. 150. And the units, the k value is the thing that had the units that was seconds. So the k value, having the seconds, multiplied by flip it, is my unit. And it wants time, so it should be in seconds. So the answer is 150 seconds. That's 2.5 minutes. So after 2.5 minutes, 95% of the reaction is done. 95% of the phosphine is different. That's a poisonous gas. Phosphine is gone. Okay. So and there it is. There's my answer. All right, that wasn't so bad. That wasn't so bad. You will have one like this. Just make sure on your equation sheet that when you have a first order and second order on your test, that you remember it's saying first order, use this equation, and you gotta have yourself a scientific calculator. All right, we'll see you back real soon for problem 4.